In this video, we're going to talk about two math topics that are closely related, vectors and complex numbers. When we're talking about vectors, this is a topic that you probably will not see until some of your upper level classes such as Algebra 2 and pre-calculus. But again, if you're not in those math classes yet, don't be concerned and think, oh, I don't need to listen to this. Maybe you can pick something up. We have a general idea of the questions that may show up on the ACT related to vectors and complex numbers. And with this review, maybe you'll be able to pick up enough to be able to answer those questions. So here's a review about really what a vector is. A vector has both magnitude, which we had talked about magnitude when we were talking about absolute value. When we were taking the absolute value of a number, we said we're really looking at the size. So that's what magnitude is. It's size. A vector has both magnitude and direction. And this is something it's array. A vector looks like array. You have looked at lines, line segments, rays early on in geometry, and a vector looks like array. The length is going to show its magnitude, and that arrowhead points in the direction that it's going. And we've graphed this here on an XY axis. You have a horizontal component and a vertical component of your vector. And vectors are usually given in this form, where we have our x component and our y component. The vector is usually labeled, in this case the vector is v, it's in bold print. You could see it written that way, or you could even see the v with a little half arrow across the top. It could be written that way as well. So in this case we're given the vector 2, 3, that's our x component and y component. And these are generally the type of questions we see. You may be asked to add vectors. And so when we have this vector, v, we have v, 2, 3, and we also have the vector w, which is 5, 6. When you're going to add them, we're just going to add the components, the x components and the y components. So we'll add 2 plus 5 and 3 plus 6, and we get that adding those vectors gives us the vector 7, 9. Same way we added, we can subtract. So again, if we're given the vectors v and w, we'll just subtract w minus v. We'll subtract the x components, 5 minus 2, and then 6 minus 3, and that gives us the resulting vector 3, 3. Now we have looked at adding and subtracting vectors. Now we can also look at multiplying a vector by a scalar. So when we multiply by this scalar, it affects the size of the vector. So let's say again we're given vector v, and we want to find 2 times v. So we're going to just take the 2 and multiply the x component and the y component by 2, and that gives us the result of 4, 6. You may also be asked about the magnitude of a vector. This could be written as similar to how we write absolute value, or you could have double bars on the vector. To find the magnitude, we're just going to take the square root of the square of the x component plus the square of the y component. So if we're given v above and we need to find the magnitude, we're just going to take the x component of 2, square that, the y component of 3, square that, add those together, and we get the square root of 13. That's the magnitude of the vector 2, 3. And that's what we talk about with vectors. That's about what we see on the ACT related to vectors. Now, corresponding to that, we also can look at complex numbers. And complex numbers are in the form, let's say z equals a plus bi. And you may have seen this when we were talking about our imaginary numbers. I here is an imaginary number. So this forms a vector, as you see in the graph, where you have a real component, which is a, that's on the x-axis, what we normally see, and an imaginary component, b, which is what is with that bi, on the normally the y component. And the point that is formed is the complex number, a plus bi. So when we see problems with complex numbers, you may be asked to multiply them together. And we would multiply the real component and the imaginary components almost like you do when you do the full method. And then we would use our properties that we discussed in the imaginary number section of I squared is equal to -1. You could also be asked to find the distance or the modulus of a complex number, and that's equal to that square root of a squared plus b squared. Again, this should look familiar. This is what we did when we found the magnitude of a vector. It's the distance of these complex numbers, and it's just an application of the Pythagorean theorem. The a component being the x component, the b component being the y component. We square those, add them up, and take the square root, and that's going to give us the distance. One other operation you may be asked to do is to find the midpoint of the line segment that joins those points. Remember, we said the a plus bi, that is a point. The real component, imaginary component forms a point. And we can have multiple points, and you may have to find the midpoint. And it's very similar to finding the midpoint of a line. We're going to look at the real component. In this case, a and s are the real components. Add those up, divide by 2. And the imaginary component is the b plus t, divide by 2 to find the midpoint. And don't forget to put the I on that. So you have, again, a point, a real component and an imaginary component to find the midpoint. So let's take a look at an ACT type example. Give this vector question a try, and we will come back and work it together. You were given the vectors a and b, and the question is, what is 3a minus 2b? So we're going to be subtracting the vectors after we have multiplied each of them by a scalar. 3 multiplied by the a and 2 multiplied by the b. So when we multiply 3 times 3, 7, and 2 times 4, 2, we get 921 for now the 3a, and 84 for 2b. We subtract those, and we just subtract the components. 9 minus 8 is 1, and 21 minus 4 is 17, and that gives us the vector 1, 17, which is answer choice B.